I recently learned I'm the first time here. It's my first time in Norway. It's my first time in Oslo, and it's my first time in Norway. I knew that first, but I learned that there is probably a larger audience tuning in a separate room where they have the possibility to choose between different talks. So hi there to you too. Today I'm going to talk to you about fast and small. What are the costs of a language feature? What's the idea behind that? Pay only for what you use is the motto I associate most and strongly with C++. And I think it was around 2005, the technical report about C++ performance got out. And it's a document I like still today because it tells us a little bit what's going on behind the scenes and which code do we actually produce. The good thing is that compilers and optimizers nowadays are really, really smart and help us to optimize our code a bit more and get rid of unnecessary, unwanted stuff. So there are many features in the language, and it's up to us to decide which one we like to use. That's the cool thing about C++. The important thing for many solutions is that nevertheless we are still close to hardware. That's also very good. However, what C++ is not is what you see is what you get language. For example, there are constructors and destructors, which are invoked silently sometimes. They can call functions, create other objects, or allocate memory. It still means that we pay only for what you use, but it also raises the question, what are the costs of the things we use really? Even with a good reason to use a feature or a library, it matters what's behind it. So what I will show you in this talk are various hand-picked selected language features, and I like to give you a few behind the scenes, so how do they work internally. So this should help you to decide which one to use or in which area you will like to use it. Let's start with an easy one, auto. The interesting thing about auto first is it's not really new. Before C++ 11, it was used to tell the compiler that a variable should be placed on the stack. Ooh, great thing. Isn't that always the case? Yes, since C++ 90, it is always the case. This makes auto the most useless keyword of all times, probably. Well, not so anymore with C++ 11. Auto got reinvented there. The meaningless reserved keyword got a new meaning. Now it does what we know from other languages, for C#, for example, as var. It tells the compiler to fill in the correct type of a variable, depending on its initialization. This is deduced by the argument on the right-hand side. This whole process itself is also old. We know that from template type deduction for years. What auto can do is it can spare us a lot of typing. That's one thing, because we do not have to write all these template parameters. We can just say auto on the left-hand side. But more important is it can save us from silly mistakes which can hurt sometimes. So for example, forgetting or adding const or getting template parameters slightly wrong in another way will result in unwanted and maybe unseen conversions behind the scenes. The resulting output may look like the same, but there may be a conversion involved. With auto, this is no longer possible. We get the same type on both sides. The deduction rules for auto are mainly to remove all top-level qualifiers, so we do not get the full-blown type with all qualifiers. Const and volatile, for example, are removed. It aims only for the underlying type. If this type is a pointer to constant memory, the constness of this memory section where it points to remains, of course. Const reference, on the other hand, is completely removed. So roughly the rules are, if you have a const tref, it becomes const t. If you have a const t star const, it becomes a const t star. The good and important news for this talk is this all happens at compile time. It's not that the initialization can change with each for loop and you get a different variable type. No, it's done like templates at compile time. So no additional runtime costs or increased RAM or ROM usage. So much about auto. Let's move on to a combination of auto and Decltype. Decltype auto. The usage of Decltype is a little bit different to auto. It's like auto to query the type, but this time including all the top-level qualifiers. To tell you up front, due to its nature, it's also compile time only. Without any overhead, as long as we stick to the rules, everything works as expected. Let's have a look at this example here. We have this ordinary program. The variable foo builds the base for it. From that, we deduce with auto and Decltype 4 new variables, A, B, C, and D. In the last step, foo is incremented by 1. So it's not the most sophisticated example here, but it will illustrate my point. And my question to you is, what is the output of the program? What does it print out for A? 1. Great, I take that. What does it print out for B? Would you agree with 1? C. 1 again, right? And D. Who has an idea about D? What's D? I have 1 here. Who wants to go with 1? Okay, I initially did 2. It's wrong. It's 2. And if you pay close attention, the only line that differs from our usual expectation is the one with Decltype auto and the braces I put in there. So they seem to influence our type, our deduced type, somehow. We put braces around math expressions, for example, and to group things. And putting braces around variables changes the expression type a bit. It's not an ordinary variable anymore. In this very moment, it's an L value. And in the context of Decltype auto, I will show you later, an L value is supposed to lead to a reference. So now, you can say, all right, nice that we have learned that, but really, who puts braces around a variable like I did here? I mean, come on, it's typing 2 additional characters, and nobody wants to do that. We got auto to type less. So I agree. Nobody does that. Some do by intent, and there's a potential that you do this by mistake. And that's if you use one feature with which I think is the one they would vote out of C++ if they had a chance to, and that's macros. We put braces around parameters of macro functions to get rid of nasty side effects for years. These braces remain in the code. The preprocessor does only do a text replacement. So the outmost braces will stick around. A popular example is such a max function as shown here. And I agree, we are in modern or postmodern C++, so that should be probably a template. But it doesn't have to. So you can get in this situation. You may have legacy code where you only switched the one side, you like to have Decltype in order for some reason, but you didn't change the other side. Then you can end up with that. That's not all. This is a slightly modified version of this no-brainer program. We simply do an x++, so we increment a variable which is passed to the macro function. And my question is once again, what's the output now? For A is trivial, come on. 1, good. B, 1, trivial as well. C. Now we have to think a little bit. 2, 1. I take the 1. It's a post increment. And D. So I get a 2. Because it's a reference. Ah, that man is good. So it's 2. It's 2 again. But there's a but. Even that the result looks the same, what happens in the background is different. Because of the nature of the post increment, we first take the variable and increment it afterwards. We need to get a temporary object. And in the context of the standard, that's an x value. An x value is an L value where you can steal its contents from. So what we get in this case is the output is 2, but instead of binding to foo with a reference, we now bound to a temporary object. That's most likely not what we want. So there's another thing you can say, okay, the program is not so sophisticated and writing x++ is not the best thing to do. We learn on other places that it's much better to say ++x. So let's pretend the program doesn't do anything at all, so it doesn't matter, we can change it. We fix that. We say ++x. We change from the post to the pre-increment. That's nice. What again is the output now? A, we didn't change anything there, it's 1. B, didn't change it, 1, 2. C is a little bit tricky, but still rather simple. We changed to the pre instead of the post increment. So I think everybody agrees that's 2 this time. And D, what's D this time? You already saw that. It's the first case again. This time it's 4, but just because we switched to the pre-increment. Due to the change to the pre-increment, the variable is incremented first and x remains, so we have a variable with braces around, and we are back to an L value. Why does Decltype in combination with auto behave the way it does? It's perfectly defined in the standard. These are the words from the standard. So we looked at case C no, sorry, at case D and E here. The first time and the third time it was E. No, sorry. The first and the second example, we got an L value, and that's why we get a reference to foo. And in the second example, we ended up with this temporary, which can be reused. So the result turned out to be different. The Decltype in auto that was in combination with auto that was my take can lead to unexpected results. It's still questionable to write such code with macros, but it can happen. And in that circumstances, it appears a bit difficult to get the correct result you like. Irrespective of that, Decltype is a compiler-only feature which has no influence on the resulting code or the performance if applied correctly, or if it matches what you want. I will show you an example later when and where it makes sense to put braces around a variable. Let's move to the next item. Do you know this type of code? It's always the same pattern. Annoying to type again and again. Plus, even that it is so simple. And we are so used to it. There's room for errors. And I'm not talking about what happens in the body. One potential error I often see is the post increment instead of the pre-increment. The slide illustrates it correctly. In some cases, it's my own code. I was taught in my early programming years to write it that way, X++. And unfortunately, this sticks till today. It's, well, meaningless, let's say that way, if you deal with an integer or so. But it matters if it comes down to objects. Nonetheless, writing X++ leads to a temporary object, as we have seen in Decltype. And this in each loop iteration. That means we construct a temporary and destruct it right after that. That's just ridiculous. It's a waste of resources. With a bit of luck, the compiler optimizes this away. Now, there's a second potential error source, one which is not that obvious often. And that's the loop condition itself. To be precise, the call to end. This function is invoked at each loop iteration. In most cases, end does not change anything because it's supposed to give you just the end element. So this means that over multiple calls, and the result of end remains constant. This is a great opportunity for the optimizer. In a very large number of cases, it sees this constantness and simply caches the value of end for us. So it does not get called with any loop iteration. Anyhow, if for some reason end does look too complex to the optimizer, it leaves it as it is. And as a result, we end up with end getting called with each loop iteration, each loop cycle. Now we are luckily in modern C++. Here we have the modern version using a range-based for loop. The first thing I like is it's much easier for the eye. It's less typing too. So all these things we programmers love. Are we supposed to react on that sound?
Just a test.
It's a test, okay. It's why? Nice. Okay. For most, this variant reduces the typing to the necessary parts, the one which changing all the time. That's nice. The other thing which is nice is that the two problematic parts are gone if you look closely. We no longer need to write the iterator increment Hence, we cannot do it in a less efficient way. In addition, the comparison to the current iterator element and end is also no longer our part. So let's hope whatever happens in the background is now as efficient as we could do it. We will look to that in a minute. It's kind of disturbing. Please note one thing, that's the colorized ampersand. With range-based for loops in combination with auto especially, this one is often forgotten. That's a little bit due to the nature of how we've written it before that. Omitting it means that we end up with a copy in each loop iteration, instead of what we more likely want, a reference to the current iterated element. So we supposedly dropped 2 possible performance penalty mistakes, and we got another one. So we are down by 1. That's good. So how does this work internally? This is the definition of a range-based for as it can be found in the standard. And it turns out that it's just syntactic sugar. The compiler does the transformation for us from a range-based for to a traditional for loop. That's nice. The important thing is that the compiler aims for maximum efficiency. It always uses the pre-increment. So it does a good job there. And it does a second thing. If you take a close look at the loop declaration, it ensures caching of the value of end by storing it in a variable. So it ensures caching regardless of the quality of your optimizer. It's guaranteed to be cached. That's a brilliant way of doing that. It's nothing we couldn't have done ourselves, but it's nice that the compiler does this for us in the background. Now, if you, for some reason, that's a side note, have an application which relies on the fact that end must be called with each loop iteration, range-based for loops are nothing for you because they are definitely to be cached. In the other way, if end changes anything, this will stop the optimizer from caching it. Here it is guaranteed to be optimized always, all the time. The whole thing is braced a little bit on the curly braces you can see on the outside. They open an additional scope for the for loop or around it, and with that the compiler ensures that all temporary variables which it declares inside of that curly braces in this scope are destroyed at the end of the loop. Applied to our example, the code internally generated for our numbers example looks like this. Numbers is our range initialization. Vector kindly provides us with 2 members for begin and end. The next step of the compiler would be to look for begin and end in the global scope. The auto-ref iterator becomes the for range declaration, and we are basically done. By the way, this version emits the same code as the one the compiler generates. So I'm pretty sure it's the same. Regardless of that, these 2 versions seem to be a little bit less efficient than the standard for loop. That might come from the fact that we have an additional variable here to cache end. So it's, I don't know, 1 or 2 instructions more. So far so good. One thing which bothered me for some time was the fact that I must have an iterator which is never really iterated. And that's due to the declaration nature of begin and end. They both must be of the same type. And to be iterable, for the iterator, it must be type of iterator. And this implies that end must be of type iterator as well, even as it is never iterated. You just need the value. Luckily, this has changed with C++ 14. That's the version from the standard of C++ 14 and 17. The difference between the two versions is the way begin and end are declared. In C++ 14, this was part of the for loop declaration. So we had a one-liner. This implies, as explained, that begin and end must be of the same type. This limitation was lifted with C++ 14. Here begin and end are declared outside of the for loop, but still within the curly braced scope. So they can be of different types. And that's now the potential that end can be just an ordinary value with no relations to the type iterator. All we need to get this still working is a comparison operator to not equal either in local or global scope. One nice thing about C++ 11 and its successors is the ability to write such a small and totally worthless, but still valid program. Here we have a Lambda which captures nothing, takes no parameters, has an empty function body, and is executed directly. So, a lot of nothing. Nonetheless, Lambdas are an interesting feature, and I think it will take us a couple of years to see all the application areas where we apply them best. They are very powerful. We can delay their execution. We can use them together with templates to parse Lambda objects to other functions, and we can execute them there. That's really powerful. So to me, they nonetheless look tiny. That example here will probably be optimized away. Optimizer will be happy. But what do they really cost? We write them inline. It's not so much we have to do for them. So to show you that, here's a slightly more useful Lambda. It should us help to see what's going on behind the scenes. Let's see what it does. It captures all variables in scope as reference. This enables us in the next step to increment x by 1 in the Lambda's body. In the following line, the Lambda is executed, and that's it. So it's not the most sophisticated code, but it illustrates the Lambda. On the right side, this is how a Lambda most likely looks from the internal view of a compiler. To be able, this class has a compiler-defined name, so we do not need to care what's the type of the Lambda, so it's unknown to us. The essential part is the function call operator within the Lambda. Our compiler is so decent to create it for us with the complete prototype, and if necessary, it also declares all required variables we like to capture either by reference or copy. Within the function call operator's body, we find our actual code we have written for the Lambda's body. By default, the function call operator is marked as const. In case we like to be able to change code inside the Lambda from a captured variable, we must make it mutable by attributing it like that. These two versions generate the 99% equal Clang intermediate language output. There's the one thing I cannot give my Lambda the same name as the compiler internally does, because it starts its variables sometimes with a $sign or just with numbers. And there's a second thing, but that does not show up in the diff. To keep it simple, to keep it small, and to keep it as the original version, I made the member variable x public. Per standard, the compiler is required to make all captured variables private. It would, for me, require a constructor to do that, and that just blows up the code. In assembler output, it boils down to a pointer. So it doesn't matter if you use a reference here or a pointer. in the illustration example, the compiler internally treats a reference as a pointer. This opens our view a bit, because we now know it's a class. And the class is a constructor and a destructor, it's an object. And the way we capture values do also matter. If we capture by reference, we increase the size of the lambda by the natural size of a reference on our platform. If we capture by copy, we increase the size of our lambda by the type, by the full size of the type. And maybe there are memory allocations happening in the background. So it's probably not that small as it looks on the first look. There are more lambdas on this slide. They're still simple. In case A to D, the variables are copy constructed. Only in E and F, we capture them by reference. And now, if you take a close look, and it's in main, that's the first look. The second look is if you take a close look at all the lambdas there, none of them is invoked. None of them. So I find it notable that only B, E, and F generate an unused variable warning, and those will most likely get optimized away. All the others stay around in your code. They cause a construction and destruction every time you pass them. What happens there on a second thought is logic. The compiler and optimizer cannot see through what we are doing here. For both, it's a valid use when we capture something which alters the outside world, because we capture by copy. That changes something. There's a copy constructor invoked or things like that. So they leave them in place. So the question is, what's different with B? Why does B trigger an unused variable warning? To answer that, let me first raise another question. What happens if we capture all in scope? That was the first thing which got me curious when I stumbled over lambdas. We capture everything in scope. That means also global variables. So doing that would make a hell of a lambda in a larger code base. So we are lucky. The compiler is our friend. Even if we say we capture everything in scope, the compiler is so decent for us to look in the body of the lambda and capture only those variables which we really use. So this reduces the size of lambda to the necessary parts. And that's the reason why B triggers an unused variable warning, because the body of the lambda is empty. And we say simply that we like to capture everything in scope by copy, but the compiler finds out that we do not use any variable in the body of the lambda, so it doesn't capture anything. That's why B triggers the unused warning. It's different, for example, in the case of the lambda D. For D, we explicitly name the variable we like to capture by copy, and that one sticks. If we name it, the compiler takes it in. In the moment we name the variable, it doesn't look in the body and optimize it away. So I consider that worth knowing when dealing with lambdas, because if they stick around for debug purposes, they can hurt. Next item, structured bindings. Structured bindings are a new feature coming with C++ 17 or already there. I'm not really aware if C++ 17 is finally out the door. Currently, they are called decomposition declarations in the standard, but there's already a proposal which intends to change the name back to the more widely used structured bindings. Structured bindings enable us to access multiple variables just with one single statement. They use the power of auto to do that. In this example, we initialize the variables x and epsilon, which hold then the variables from our point struct x and epsilon. The array notation gives us a clue that we get more than one value. It's array syntax. Currently, it's impossible, and that's by design, to skip values in between, like it's possible with .tie. It uses .ignore for that. It was decided that for the first draft of for the first release of structured bindings, that shouldn't be possible. So how do they work internally? Everybody who was here for Nikolai's talk earlier this day got a glimpse on that. That's roughly the code generated by the compiler. First, a temporary hidden variable is created. And this gets our PT, our point, assigned. Afterwards, the compiler creates two variables, x and epsilon, for us, just as we asked. They are filled, of course, with the value of our point struct. The interesting part is they are more like a reference to the insides of our point, of our temporary. And the whole magic of getting the variable happens with get. Get looks like a template which takes a parameter, it's an index ranging from 0 to n-1. We can also make the capture on the variables a reference. Then we add on the left side the ampersand. What's changing in the background is on the right side that the temporary variable which is created is a reference then to our point. And I was a little bit surprised when I first realized that, because I didn't think that there was another variable constructed. That means that we have a copy construction happening there in the background. I was under the impression that I get a copy of x and epsilon and not that there's another object resulting first. So, how does the compiler do that? To find a decomposition, the compiler takes 3 steps. First, it checks if the object in question is an array. This is the simplest form for it. All elements are accessible by default, and the compiler knows their size and all the other things very well. In the case it's no array, the compiler looks in step 2 for the simple tuple size in the namespace stud. And in the last and in the final step, the compiler checks if the object in question is a class with only public members. If none of that is true, you cannot use structured bindings. This raised the concern to me that the whole feature works only well with public classes, and from my point of view, that's not what's a class for. A class is to encapsulate stuff and not to give world access. So I asked myself, how does this work with classes with private members? And I came up with a solution. It's simple. We just have to make the compiler happy. So for that, let's use an example point class here. It's nothing new. I just changed from int to double to confuse you a little. And because I think it's the example of Scott Meyer's point class in his most recent book, Effective Modern C++. So that's the base. And how do we make this class decomposable? We need to make the compiler happy. And the compiler is happy when it finds a symbol called tuple size in the namespace stud for our class. So let's give it to him. There are two ways. That's the naive one. In this tuple size, the compiler looks for a member value, for variable value. The version 1 down is the probably much better one because it uses the standard library, stood integral constant, and this brings all the elements necessary with it. So now we have the symbol which tells the compiler how many variables are in our class to be decomposed, and we need two more template functions, and the compiler uses them to get the type of each variable it tries to get out of our class. In our simple example, that's double for both cases. So apply to our example, if we put it together, it looks like that. The gray part is from the point from before, and the colorized part is what you've seen on the slide before. So there's one thing missing, and that's the get itself. There's no get here. So we need that. That's the version with get. Get is a template function. And as we like to have access to our private members, it's within our class. Other possibility would to provide it in global namespace. Here it is in our class, and it uses another very cool feature of C++ 17, the const expr if. This whole get is completely const expr. It completely happens at compile time. We know the index of the element we like to access, and with the const expr if, we can reduce the size of the function get to only the necessary part. In case of index 0, it's only return m epsilon. In case of index 1, it's the member function call to get x. So that's cool, that's nice. Let's get crazy for a moment. Let's say, okay, now we've did all that work, but we like to give out a reference to our internal variable. Let's say m epsilon. That defeats the purpose a little, but let's do that. How do we do that? We have Decltype auto. Putting braces around a variable in combination with Decltype auto gives us a reference. So that way, we have also a function which returns two different types. First time, a double. Second time, a reference to double. That's powerful. Let's come to a more well-known feature. What do we know about static? We have that for a long time. But what do we know about it? There are simple things. There are roughly, roughly 4 application areas. A global variable can be marked as static. With that, the lifetime of the variable is extended to that of the program. Its scope is also reduced to the current compile unit. We can put static on functions. We can mark them as static. Then their visibility is reduced to the current compile unit. This gives the compiler, by the way, potential for several optimizations about a function. The static can also be applied to a member function. In this case, the function exists without an object of the class itself. It's one case we use often. And last but not least, static can be applied to function local variables. So we can have static local variables within functions. And they are a bit special. They also have an extra paragraph in the standards. That's how they are described there. Local variables, that's what a standard defines, are initialized the first time control passes them. And that's especially the feature we like about them, and I think why we use them. So let's focus on that. How does this work? The words in the standard are pretty simple, especially for us developers. I like them. It's the job of the compiler. I do not need to know, but I like to know. So how does it do that? Even a compiler needs to keep track of which variable was initialized, which not. So this information needs to be stored somewhere. Cannot come from nothing. To keep track, the compiler, and that's conceptual code only, the compiler introduces a new, additional, and for us, hidden variable. Let's call that compiler computed. Given that the compiler is generous with us, it uses a bool for its type, which is set to false by default. Next, the compiler dissects our static variable a bit. Instead of writing it as we would do, it reserves part of memory with the size of our object we like. In addition, it introduces a new if. And this one uses the variable generated by the compiler to detect whether the variable was initialized or our static was initialized or not. And in case we pass that if the first time, the compiler, that's the conceptual part, I'm not sure, but calls the placement new to invoke the constructor of the class, and we are fine. Afterwards, the compiler sets its own variable to true. The order here is important because the standard also requires that we get a do-over in case the initialization of our static fails. If the constructor throws, we should be able to pass that function again and again and hope that it will work after some time, or the second time maybe. So to maintain the exception safety, the order is important. The variable is set to true after we successfully constructed our object. So this static caused headaches for many developers over the years. As you can see, there's absolutely no thread safety available, and that's the best version of the static you can get, the ones where you handle pointers and use new yourself, they are worse. So that's the best one. Since years, we are looking for methods to guard this section against concurrent access. And the really good news is, since C++11, we no longer need to take pain pills. This single sentence is a game changer. As part of C++11, it changed our world for static. If control enters the declaration concurrently while the variable is being initialized, the concurrent execution shall wait for completion of the initialization. Beautiful. Now this nasty logging part is job of the compiler. Let it deal with it, go home, wonderful. Thread safe. That's not so an easy task for us all the time, so how does the compiler do it? Based on the example from before, our bool increases slightly to an integer. The lower byte of the integer is still used as a bool to keep track of the initialization state. The remaining parts are used as a mutex or atomic log. That depends on the implementation. So we also got another new if. This uses a function called seeks_are.Guard acquire, and we have a seeks_are.Guard release afterwards. And they both take this compiler computed variable. Behind mainly the seeks_are.Guard acquire function happens, well, the magic. It depends on the configuration, for example, of your GCC, G++, or Clang, what they believe or what you have configured them, what is your threading environment. they either use a mutex or, as the last resort fallback, they use atomics to guard the section. And they are also kind with us because that's an operation with some costs. It's maybe slow, it may be delayed to get that lock. So this is only done in the case the variable is really not initialized. In all other circumstances, we are fast. So that's wonderful. We've got that out of our bag. We can be happy we have thread-safe statics now. I'm in the embedded field. I know a couple of operating systems which are rather small, which are not Linux-based. They are for tiny processors. There are environments where you have your own logs. You know exactly what you're doing. Your static is already guarded because you need to guard a much larger section. There are also environments where you're single-threaded. Just one thread. Doesn't require a log. So, but now the compiler throws in this log. That's good for all the people working in a multi-threaded environment, but for the ones in a single-threaded environment or for those who are controlling their environment precisely, I don't know. The interesting thing is GCC generates code like this since 2005. It was just not usable that much for us because it was only GCC and it was a GCC-specific enhancement, so it was not cross-platform or cross-compiler compatible. And when they introduced this feature, there was a kind to add an option F no thread-safe statics to make it go away. So that's the solution I hope other compiler vendors provide as well. There's a dirty hack you can do, at least for Clang and GCC. The symbols CXR-guard acquire and CXR-guard release are intended to be overwritten by your standard library. So the compiler provides them only if there is no existing symbol for that. So a really dirty trick is just provide them yourself and implement them empty, and they will go away. But that's just if you're controlling your environment and you're knowing what you're doing. This also applies only if we are dealing with objects. And to be specific, objects with a non-trivial constructor or destructor. Let's switch here. We have this singleton still. We have the static in there. And it's a bit more complex. I take an instance of that singleton. It has a set and a get now. And in the set, I pass argc, and that's just to get the optimizer off my back. I don't like this part to getting optimized away, and then I return the get. So that's all. And that's a good one, because that's a class with trivial destructor and trivial constructor. We will have no log there from the compiler, because it doesn't matter for us. We cannot see if this code is initialized the first time we pass it in a function or at the start of the program. Doesn't matter. What's missing here is we've written so much code to have this singleton, and where's the constructor? The constructor is the default constructor, and that's public. So we have the potential to have several singletons, which defeats the purpose of the name singleton. We can fix that. And an attempt to fix that is to make the constructor private. So we're defining it ourselves. This gives us also the potential to initialize x to a well-known value. And that's the point where we end up with the logs again, because now we've provided our own constructor. The class is no longer trivial from the perspective of the compiler. It will start generating the logs because we provided the code, so it's on us to know what we are doing. We can work around that with the equals default. We can say, yes, please, we like to have our constructor in the private section, but compiler, please do provide implementation. This counts as trivial for the compiler, so we will have no logs. They are introduced by the compiler. Of course, the same thing is possible for the destructor. We can do it in the less efficient way by providing the empty curly braces. Then it's a constructor provided by us, with code by us, even if we have not really written code there. We can fix that with the equals default. That works too. It stops working if for some reason we declare the destructor virtual. If we have some application where our singleton needs to be a base class for something, even the equals default does not help us in this case. If we have a virtual destructor, even if defaulted, it is a non-trivial object for the compiler, and it will generate the logs for us. So, that's all from my side. My name is Andreas Fertig. Been a pleasure giving a talk to you today. I'll be around for questions. Either, I think we have about 3 minutes for questions here, or at the conference, I'm here till Friday. Have a nice lunch in case you have no questions.